Hello and welcome back. In this video, we're going to introduce the row space and the column space and the rank of an m by n matrix. Let's start with the definitions. So if A is any m by n matrix, then the row space of A is just the subspace of Rn that's spanned by the rows of A, and the column space of A is a subspace of Rm spanned by the columns of A. Let's take a look at an example. So suppose we have this matrix A. The first row is 5, -3, 2, 1. The second row is 3, 1, -1, 2. And the third row is -1, -5, 4, -3. So this is a 3 by 4 matrix. And we can see that the rows of A are vectors in R4, but the columns of A are vectors in R3. So the row space of A is the span of the 4 rows, 5, -3, 2, 1, 3, 1, -1, 2, and -1, -5, 4, -3. It's the span of those 3 vectors. And we know that's a subspace of R4 because everything in the span of those vectors is a linear combination of those vectors. And it will be closed under addition and scalar multiplication. The column space of A is going to be the span of the 4 columns, and those are in R3. And note that we didn't say that these vectors were bases for R4 or R3. We didn't check for linear independence. So we know that those 3 rows of A do span the subspace, but we don't know if they're linearly independent. We didn't check that. But we're interested in bases for these subspaces. So let's look at A again. And if we do Gauss-Jordan elimination on A, what we're doing is adding scalar multiples of one row to another, or just multiplying one row by a scalar, or swapping rows. And so what we get is a brand new matrix. So if we put it in a calculator, get reduced row echelon form, this is the new matrix I get. It has completely different rows. It's only got 2 non-zero rows, in fact. And the row space of this new matrix turns out to be the same as the row space of the original matrix because of the elementary row operations. We didn't actually change the subspace. So the rows of B are just linear combinations of the rows of A. So that gives us this theorem, Theorem 4.13. It says, if an m by n matrix A is row equivalent to another matrix B, then the row space of A is the same as the row space of B. But furthermore, take a look at the rows of B. The only 2 non-zero rows, we can tell by looking at them that they're linearly independent, right? You can tell because where there's a leading 1 in one of the rows, there's just zeros in the rest of that column. And that's true of any reduced row echelon form matrix. Wherever you have a leading 1 in your reduced row echelon form, there will be zeros in every other entry in that column. And so there's just no way that row with a leading 1 can be a linear combination of the other rows. So we get another theorem from that. If a matrix A is row equivalent to another matrix B, and B happens to be in row echelon form or reduced row echelon form, then the non-zero rows of B form a basis for the row space of A. So if we want a basis for the row space of a matrix, all we have to do is put it in reduced row echelon form or just row echelon form and take the non-zero rows of our new matrix. For our matrix A, a basis for the row space of A is just the 2 rows of B. So the first row and the second row. We could have figured out which rows of A were linearly independent, but in order to do that, we would have to do Gauss-Jordan elimination anyway. So we'll just take the non-zero rows of B. it spans the same subspace as the rows of A. Well, what about the column space of A? Well, we did elementary row operations. We did not do elementary column operations. So the column space of B is totally different from the column space of A. So we can't take the linearly independent columns of B and say that that is a basis for the column space of A. However, when you do elementary row operations on a matrix, the columns of the new matrix have the same linear relationships that the columns of the original matrix do. What I mean is, if we look at the columns of B, we can see that the first two columns, I'll call them B1 and B2, are linearly independent. We can tell by looking at the matrix that those two columns, they're not scalar multiples of each other, right? And we can also tell that the third column is just a linear combination of the first and the second column. And also the fourth column is a linear combination of the first one and the second one. Those linear relationships are the same as the linear relationships of the columns of A. So if I look at the first two columns of A, A1 and A2, I know that those two columns are going to be linearly independent, and I know that the third column is a linear combination of A1 and A2, and the fourth column is also a linear combination of A1 and A2. Since A1 and A2 are linearly independent and they span the column space of A, I know that those two columns form a basis for the column space of A. So the column space of A has this basis, the first column and the second one. All right, there's another way to get a basis for the column space of A. I could have just taken the transpose of A and then found the row space of A transpose. Might give me a different basis, but it'll be the same subspace. So notice that both of these subspaces have the same dimension. They both happen to have dimension 2. That will always happen. There's a theorem, Theorem 4.15, which says that the dimension of the row space of a matrix is always going to be the same as the dimension of the column space. And that dimension is so important, we give it a name. It's called the rank of the matrix. So for our matrix, the rank of the matrix is 2, because it's the dimension of the row space and the dimension of the column space. All right, that is how to find a basis for the row space of a matrix, and one of the methods for finding a basis for the column space of a matrix. And also, we've demonstrated how to find the rank of a matrix. And in the next video, we'll explore a third subspace associated with the matrix. The third subspace is called the null space, and I'll see you in that video.